Yeah, very good. Okay, thank you, John, and hello to everyone. When John mentioned 30 years, I was doing a little bit of an add up before, and I realised that I started in this area in 1975, so that's getting frighteningly close to 50 years, which is a bit of a shock. But my first, I was doing a project at Melbourne University in marine botany, and I was actually looking at the characteristics of one particular species that we thought was a native red alga. Well, it turned out some times later that it was an invasive or it was an introduced species from Japan. And then I went on to work on the fouling community, the algal component of that, on a structure just outside the port of Melbourne. And no one had really looked in that area before. My first scientific paper was actually on the first discovery of a European species in the port of Melbourne. So my fate was destined, and little did I know that invasive species would come back in the year 2000 as a prime area of my interest on top of fouling. So the biofouling diaspora. I'd like to start by repeating a quote that was made by Mike Hadfield back in '99 at a conference on marine corrosion and fouling we're having in Melbourne. And that was that the marine world of 10,000 years ago was not characterised by ships, barges, docks, floats and pilings. Most of the invertebrate species typical of the fouling community are never found elsewhere, and most exist only on substrata where tidal exposure does not occur. In the pre-maritime human environment, this habitat must have been restricted to natural floating materials, mainly the drift logs, most abundant in bays and estuaries. And this is really a key point, because over the many years that we have been sailing our seas, the biofouling community has essentially evolved by picking up species from different parts of the globe that were suited to that life on the bottom of ships or boats. Now, the other point I'd like to make before we start in talking about it is this differentiation between what is a non-Indigenous marine species and what is an invasive marine species. And it's quite important, because a non-Indigenous marine species is really any species that's transported by human activity, intentionally or accidentally, outside its native range. Now, many of those cause no harm at all. They often just become benign elements of the native community. Whereas an invasive marine species is the subset of the non-Indigenous marine species that actually causes a significant impact, be it to the environment, to the economy, to human health, or to social and cultural values. So that becomes when we start to look at the various species that are transported on ships and establish in new areas, there's quite a difference between those two, and we'll explore that a little bit later on. So if we go back in history, biofouling has caused problems to mariners for as long as mariners have been mariners. So if we go back to the 1st century AD, Plutarch talked about how it was usual to scrape the weeds, ooze and filth from the ship's side to make them go more easily through the water. And that is something that has proceeded through the centuries since. Now, people tried to find ways of actually not just having to scrape the hulls to get rid of the growth. And it was the ancient Grecians who first applied lead sheathing, which had some effect, but it was still more to do with stopping the shipworms, which are the molluscs that actually drill into wood and create tunnels through it and can sink a ship. And so through until in the 16th century, Spain, France, and England were all using lead sheathing on their wooden ships. And as far as anti-fouling management, it wasn't until the copper sheathing was introduced in the mid-1700s, initially on there's a floating A there. It wasn't the HMAS alarm, it was the HMS alarm. The Australian Navy hadn't quite set themselves up in 1758. And that was actually, it's said that in the Battle of Trafalgar, the reason the British ships had an advantage was the fact that they had copper sheathing, so they didn't have the fouling growth that the Spanish fleet had on their hulls, which slowed them, and so the Royal Navy was far more manoeuvrable. However, copper sheathing continued on until the introduction of iron ships, and because of what's called galvanic corrosion, if you put copper on iron, you'd end up with the iron corroding away. So at that particular point, it was almost thought about the end of moving into iron ships because they couldn't protect them. The common method right through a lot of this period was still what they call careening. And the photo behind and in the introductory photo showed how, without any anti-fouling protection, to get rid of the growth, you basically had to take the vessel out of the water or float it onto in the shallows and tip it on one side, scrape all the growth off, then tip it over the other way and scrape that side. Now, the photo in the background of this, or the painting in the background of this slide, is actually quite relevant to someone in Australia, because the Astrolabe and the Zélie were the French scientific expedition ships, and these particular vessels circumnavigated Australia and investigated the Pacific between 1837 and 1840. Now, this picture shows them up in the north of Australia in Torres Strait, where they're actually scraping all the growth off. Interestingly, the leader of this expedition, a Frenchman by the name of Dumont d'Urville, in Australia now, the bull kelp, the large kelp that grows along the southern coast of Australia and also in New Zealand and other parts, even across South America, is the scientific name's D'Urvilla, so it's named after the leader of this expedition. Now, the paints came into use. They tried various things early, going back to 400 BC, where arsenic and sulfur were mixed with oil. But it was in the 1860s, about this time, that the iron ships were coming in, that the first actual paints were developed. And initially, 1860, you can see a mixture of hot soap with copper sulfate was used. And then, 1863, a copper oxide in tar with naphtha, followed by various formulations of copper, arsenic or mercury compounds in a solvent, turpentine, naphtha and benzene, and in some sort of matrix, so shellac or tar. And essentially, that type of formulation persisted right through until the 1960s or 70s. Essentially, and we still use them, copper compounds. Today with secondary biocides, they have a solvent, commonly xylene, and they have some sort of polymer matrix. For many years, natural wood rosin was used as the polymer matrix because that had a very slow dissolution rate in seawater. So we've had, how many centuries we can add up, where there was essentially no biofouling protection. And so vessels could carry things all over the world. Now, as an indication of how ineffective these were, this is a dry docking report from 1943 in a little booklet that the Iron and Steel Institute put out in the UK. And they've got an example of a dry docking report. And now if we look, we can see that this dry docking was in November 1943, and it had previously been dry docked in March 1943. So, we're only looking about 8 months. In that time, the vessel had left the UK, gone through the Suez Canal to Australia, and then come back via South Africa to Liverpool. And when it dry docked, we looked at, the comment was that fouling was generally heavy with barnacles, chiefly on areas for which the anti-fouling coating had failed. And the categorisation is that the barnacles had much, there was much green weed, And then there was little tube worms, mussels and oysters, hydroids, weed. And this is how all the ships in the world would have been. They would have all been carrying a huge amount of fouling on all their voyages. So if we start to look at the species, Charles Darwin, some people think he's renowned for his origin of the species, but he's actually renowned for his monograph on barnacles, which actually was one of the reasons he didn't get around to publishing his origin of the species until he was virtually jolted into it by Wallace developing a similar theory. But in his monograph in 1854, you can see he got a lot of his specimens from the bottom of ships. So Ballast tintinabulum on the top was arriving on many ships from West Africa, the West Indies, East Indian archipelago and China. And this next set of Underballast amphitrite, most of these are now considered separate species, but we have them all coming quite abundant on ships' bottoms. And the last one even coming to Europe from the east coast of Australia. And then we had other species such as Ballast, which until fairly recently was considered a high-risk species to Australia, but back in the 1850s, it was quite common on vessels plying across the Atlantic coast. And then there's a list of other 5 more species down the bottom, which Darwin recorded off the bottom of ships. Sorry, it's tending to respond slower than my click. I'll just get back to where I should be. Okay. Now, if we jump forward from Charles Darwin right up to the 2000 and plus this century, and Graham Inglis and his team in New Zealand did a survey of ships coming into New Zealand, and they identified all the species that they found on those ships. Now, on the international commercial ships, they surveyed 270 ships. And if we look at what we've got growing on it, the top 13 species were all barnacles. And we actually get down to number 23 before we actually get a non-barnacle. And those barnacles that are highlighted, the species that are highlighted there, were actually species that were recorded on ships by Darwin. So, you know, there hasn't been a huge change over that century and a half. And on the right, if we look at a breakdown of all the species groups that Graham and his team found, we can see that the barnacles accounted for 58% of the species, with the hydroids, the Cnidaria sort of, and other small crustaceans coming in after that. Now, the other, what I call the Bible of marine fouling and its prevention, was put out by the Woods Hole Oceanographic Institute in 1952. Now, when you looked at the docking report I put up recently from 1943, during the Second World War, it was realised that the anti-fouling protection of naval vessels was having a huge impact on their operation. And so the Woods Hole Oceanographic Institution, in collaboration with the Navy, put together a massive book that covered virtually all aspects of biofouling and anti-fouling prevention at that stage. Now, they actually, one of the chapters is effectively a census of all the species that they found recorded in studies on biofouling. So they've done a huge literature review. And what they found was they recorded nearly 2,000 different biofouling species. Now, of these, 374 species were recorded off ships. There were more on buoys, and there's a navigational buoys. Now, I'll talk about this later, but again, the difference between a ship and a buoy is the buoy stays in one spot. It doesn't move around, so it doesn't have the the stresses that's imposed on a ship when it sails across oceans. And therefore, a much more complex biofouling community can develop. And they're also not as, at that stage, they weren't taken out of the water for cleaning as regularly. And the biggest numbers, test panels, is 655 species, and that's known now. A lot of people studying fouling, they'll put panels in the water in a port or harbour and they'll pick up a lot of species that way. If we look on the right, the breakdown of different groups of species is quite different to what was shown up in the English study. And when I look at this, you know, the barnacles are 17% compared to, we had 58%. But I put this down to probably an effect of the anti-fouling paints that we use today, that this pie chart is just from the species that Woodsole found on ships, and it shows a much more diverse community. So I believe that, you know, the anti-fouling paints we have now actually greatly reduce the number of species found on the vessel overhaul, which makes sense. Now, if we go back in history into Australia, you can see that a lot of species arrived early on, and particularly in the gold rush years, around about the 1850s. Vessels were coming across from Europe, from all parts of the world, and a lot of them were just abandoned in our ports, such as Melbourne, because the crew all ran off to the gold fields to make their fortune. And some of them were actually turned into prison ships as well. So you had these wooden ships coming in and just sitting there, giving the opportunity for things to spread off. And if we look at these species, which are all still fairly well-known biofouling species, we can see that, you know, Hydroides elegans, a worldwide species, was first described as a species from Sydney in 1883. Now, around about the time it was described under a different name from Italy, and you can fairly sure that at that stage it had come from Italy to Australia rather than the reverse, and it's actually likely it went from Japan to Europe first. Up on the top right, the vase tunicates, the Ionia intestinalis, was first recorded in Sydney in the 1870s. We have the hydroid Ectoplura crocea, first described in 1884. Now, in 1999, Chad Hewitt and the team had an extensive study on non-Indigenous species in Port Phillip Bay. And a little summary in that is that graph in the bottom left-hand corner. Now, for some, that may indicate that, yes, the rate of invasions increased greatly since 1950. But in actual fact, it's more a reflection of the extent of study of the invertebrate fauna and flora of Port Phillip Bay. Now, around the 1850s, you had some quite keen naturalists looking at a few different groups, but there were no more detailed studies, thorough studies of Port Phillip Bay until a very detailed study in 1960, and then another one in 1970. So it was really a case of when you start looking, you'll find things rather than there being a pulse of new invasions in the last half century. And if we look today at the impacts of some of these species, this is Port Phillip Bay, this is the hydroid Ectoplura, and this is the effect it has on the mussel ropes from the mussel farms in Port Phillip Bay. And similarly, excuse me, over in Scandinavia, this is a photo from Norway, again showing the same species growing all over the fish farming nets. The vase tunicate, which is the one I mentioned up here, introduced to Sydney in the 1870s. This is actually a photo at the top of mussel farm in Canada, it's on the west coast, Edward Islands, I think it is. And here we have it on the bottom on a tug in South Australia, spreading and growing there and causing an issue. And of course, we have the tubeworm Hydroides elegans, which is spread throughout the world and is one of the major fouling species. And here we have it inside a a pipe on an Australian submarine, and here on the side of a crane barge in Sydney Harbour. And this particular species is renowned for fouling propellers because it actually likes a little bit of copper, and the amount in an alloy is enough to stimulate it to settle. Now, it hasn't all been one-way traffic. We have two species that were introduced to Europe in the late 1930s, 1940s. And the barnacle Ostrominius, previously known as Alminius modestus, has spread right round the intertidal coasts of many of the countries in Europe. And that sort of tied in with the Second World War, where you had the troop transports all heading northward to take our soldiers across to war. This tube worm, Ficus is an interesting one because it's become widely known as the Australian tube worm and introduced to Europe, supposedly from Australia. But in actual fact, the evidence suggests now that it was introduced to Australia. It's not an Australian native and possibly came from the Northwest Pacific, which has been an origin of a lot of species because it's a centre of diversity. Now, if we jump forward to the last couple of decades, if we look at species that are associated with biofouling that have been introduced, we have three notable ones here. One, the Mediterranean fanworm. Now, it was first detected in 1965 in Western Australia, and then sort of spread to the other states. And it has also now been spread across to New Zealand. We have the Japanese kelp, which is widespread in Europe, being introduced there along with Pacific oysters for culturing. And we had it first introduced in Tasmania in 1988 and then to Victoria in 96. Now, interestingly, they're two very different haplotypes. And it seems that the 1988 introduction to Tasmania was probably in ballast water of a wood chip vessel, whereas the Victorian introduction most likely came from New Zealand, where it was thought to be introduced by a Japanese fishing vessel. And more recently, we have the Guadalupe turatura, another one widespread in the Mediterranean and probably introduced by with the oyster imports, first found in Tasmania in 2004 and then spread presumably by biofouling to Victoria, New Zealand, New South Wales. And one of the important features of these species is that none of them have had a huge impact. They tend to be confined to disturbed areas where they can establish, but they can't invade or cause large populations that displace the native communities. Now, this is a well-known histogram that was put together by Chad Hewitt and Marnie Campbell back in 2010, which compared the various vectors for introducing species, and the three locations are San Francisco Bay, Port Phillip Bay and New Zealand. Now, the thing that this has been misinterpreted by many people as introducing invasive marine species. Now, if you remember the start, I said invasive marine species are species that caused harm. Now, most of these biofouling species goes back to the 1850s that they were introduced, and virtually almost none of them have had an impact. They're all pretty well benign. You find them as components of the inshore area around the port or growing on jetty piles or things like that. So a prime example of this would be Undaria. When we get to ballast water, things are a little bit different, and this particular sea star, the Pacific sea star, was introduced initially to Tasmania, then to Port Phillip Bay in ballast water, and it has had a huge effect, a huge impact. There are millions of them in Port Phillip Bay, and they munch just so many different things. If we get on to aquaculture, species like this, the codium, which again is widespread around the world, most likely introduced with oysters. Again, it has an encrusting crust that forms on the oysters that can regrow into a plant. So probably an associate of of aquaculture. Then intentional aquaculture, well, the Pacific oyster. I mean, this is causing problems in Australia. It causes huge problems in Norway, where it's gone feral. And our last little guy, the European green crab, which probably came in semi-dry ballast, which was pre-ballast water days, where they loaded the bottom of the hull with rocks off the shore, and the green crab probably survived across to Australia in that ballast. One big difference, if you compare ballast water and biofouling, is that the ballast water picks up a whole volume, a whole community in one place, and then carries it in a protective environment to another place where it was discharged. So this is where I see that a lot of the harmful species, the red tides, microalgae, and the Pacific sea stars and the zebra mussel, were carried across to new locations and were able to take off. Whereas the biofouling is very much controlled both by anti-fouling and the rigours of life on the bottom of the ship. The equivalent to, the biofouling equivalent to ballast water is probably along the lines of the harbour pontoons that floated across the Pacific Ocean after the tsunami in Japan and beached on Canadian shores with a full community on them, which included crabs and other species, but this is not what you find on vessels. So if we look at ship biofouling species, the ones that have developed into this community, they have attributes of broad environmental tolerance. They are highly fertile. They can hang on. Some of them actually settle preferentially on floating surface. A lot of them are biocide tolerant, or some are actually attracted to a small amount of biocide, such as copper. They're opportunistic settlers. So if there's a spare space, because they are highly fertile, they can take that space. And they are what they call selected, in that they are short-lived, highly fertile, but can't compete against slower growing things. So an example, this goes back to work I did back in 1979, where we were looking at marine growth on panels on the right. And this is a progression over more than a year. And you can see the change in community with time, that initially we've got the little turfing species, and then the bryozoans come in. And then towards the end, we're starting to get the slower growing sponges coming in. And after that, the molluscs and corals actually started to appear. So what we see is that most non-Indigenous marine species that come as fouling are largely confined to artificial surfaces. So you only find them on the piers and pylons and rock walls and all the non-natural environments, or in a disturbed environment where a healthy ecosystem can't develop. Some species that are thought of as a great risk are the green mussels, but they tend to be regionally limited. So Perna canicularis, which is the New Zealand green shell, has never established in Australia. There's been a few incursions, but it's that natural biogeography that holds it there. And the Asian green mussel, Singapore, for instance, it's only found on the north side of the island, which is highly productive waters. So when you start to talk about what is the environmental impact of biofouling non-Indigenous species, there's little evidence that they actually invade healthy ecosystems, and they're largely a secondary environmental impact. That car in the centre is actually the biggest settlement plate I've ever seen. That was when they were recovering all the dumped cars out of the Maribyrnong River in Melbourne, and this one was completely covered with Mediterranean fanworms. And if we think about, the secondary impact, on the right, we have an artificially built marina and harbour in Western Australia, where if you think about what is the greatest impact there, is it the harbour itself, or is it the fact that you're getting some non-Indigenous species growing within that harbour on the pontoons? Now, I think that international transport isn't a huge issue, but domestic transport is. And this is a figure of the Japanese kelp when it's spread in Port Phillip Bay, where it's established around the northern part of the bay, and then all the distribution elsewhere is by small boats to piers and structures elsewhere. So it hasn't spread along these shorelines. And the top right actually shows a vessel that used to sell mussels in the Port of Melbourne, moved down to Port Arlington, and the little Undaria is growing on that ship. And similarly in Queenscliff, which is at the mouth of the bay, 2012, this particular yacht was taken down to the marina and just left. And it was growing Undaria, but the authorities had no way to get rid of it. A similar risk comes from the vase tunicates, where we saw, I was involved in an inspection of a tug that had gone to Port Lincoln, and it within a few weeks had vase tunicates all over it. Now, I believe this is due to Port Lincoln's, where they have the big tuna farms, which are a prime location for a nursery ground for the vase tunicates. Now, what you can have, this is a boom and bust species. So this tug comes around to Port Phillip Bay, where the mussel farmers are, and actually can stimulate a new big bloom of vase tunicates, which could devastate the mussel crop for that year. So what do I see of the impacts of biofouling and biofouling non-Indigenous species? Well, on vessels, it's the costs. You know, this is why we have to dry dock vessels, how we have to use anti-fouling coatings, how we have to clean them. It increases their drag, so it reduces their speed, increases fuel, and then it can cause failures in seawater cooling systems. To the environment, I see the biggest impact of biofouling to be towards climate change, in that the additional fuel you need equates to additional emissions of not only greenhouse gases, but also the sulphur and nitrous, SOx and NOx. To the economy, most of the damage is to an impact is on industrial maritime infrastructure, so growing on piers and pylons or in cooling water systems for power plants, but more so in aquaculture. Essentially, you're putting out a surface that you want to biofoul, but you want it to biofoul with only the right species. So if you're growing mussels, you only want mussels. You don't want vase tunicates or hydroids. And then, of course, there's this big problem of the domestic spread of non-Indigenous species. So my list of conclusions from all my years of looking at this is that, yes, the character and composition of biofouling is quite unique. And the spread around the world has been facilitated by shipping over many centuries with virtually no control through until, or decent control through until the late 1960s. And I consider that the introduction and establishment of invasive marine species as vessel biofouling and international transfer is extremely rare. And few of these biofouling species actually cause adverse environmental impacts. And in most environments, their abundance and occurrence is a secondary impact of coastal development disturbance. I don't see that international trading ships are a major vector for invasive marine species, but domestic vessels, yes, definitely for spreading things around the coast. You saw that when we got the kelp in, it got spread around the coastline, and codium got spread from Sydney to Western Australia. But they can impact significantly on shipping, causing increased costs, and on aquaculture, and particularly the increase in fuel consumption. So despite the first 3 to 5 points, there are significant benefits to achieve through better biofouling management to address points 7, 8 and 9. And this is where I see the IMO biofouling guidelines as a very important document. I have one last request, which I'd like to ask of all of you. Some of you have seen this previously, but I'm conducting a survey to work out which species are considered biofouling species to be important worldwide, and in some areas they may have significant impacts. So I'm asking for each one of you to actually think of the 3 species they would consider that are biofouling species that cause high impacts, and just send those names to me. And to date, this is the result, where we see that there's a group of 7 species that stand out that people have nominated, which are high impact. And I will look at those species and sort of then thoroughly review them. And so with that, I'll hand back to John to manage question time, and thank you very much.